Hello, everybody, and welcome to the 39th Annual Symposium on Telescope Science. This year, a joint meeting with SAS and AAVSO. We will get started momentarily. Jerry Foote, as MC, will declare when it's exactly 1800 UT, and we'll get moving.
Looks like we have about 100 people online right now.
Neat.
I would put out that there are some questions in their poll. You have a little poll button. There's some questions in there. Where you're from, what do you do, how do you like us? A series of questions. You might look at those at your convenience and try and give us some feedback.
Oh, we get to those shortly. That doesn't happen until I turn them on.
Oh.
Get this feeling of malevolent power.
Okay, start recording.
Okay, we should be recording. How do I confirm that?
I've got it on right now.
It is being recorded. Kaylee has a question already about, does this function as the chat? Hold that question. I'll get to it as part of the introduction. Should I be starting now, Jerry?
Yes.
Okay, and Bob Gill, do I have keyboard and mouse?
Yes.
Perfect. Well, welcome again, everybody. Thank you for joining us at this first ever attempt at an online symposium. You can't see each other as attendees in the webinar. With any luck, you are seeing a handful of us across the top of your screen. If you don't recognize me, that's me waving my hand. There are 129 and growing people in the audience right now. A total of over 200 have registered. So I would like, before getting started, to try a little poll to see if we can find out who is here and where you're from. Now, launch. So you should be seeing on your screen, those of you who are in the audience, not the panelists, a poll asking where you're located. Feel free to click on that appropriately for yourself. The system will compile the results, and in a couple of minutes, if I can find the right button, we'll see what the results are. Logistics for you attendees. If your internet goes down, you can use your personal URL that was emailed to you by GoToWebinar to rejoin when the net comes back up for you. Or if you're down for several hours, when you use that same URL, what you should be brought back into is the recording of this session. Near the top center of your screen, you have a couple of controls. You can move the webcams of the panelists to the top, right, bottom, or left of your screen, whichever is most convenient for you. And there's a button to either exit or enter full screen mode. If you want to do something else during the webinar, certainly you're not going to be checking your emails, but if you need to change the volume on your headset or something, you go to outside of full screen mode and you should have access to the rest of your computer. Okay, let's see. I'm still seeing responses come in. Okay, I'm going to see if I can close the poll and we'll see what the responses are. Well, I don't see the answers. Well, okay, but the answers are 80% of you are from the US, 3% from Canada, 11% from Europe, including the UK, 2% from South or Central America, and 4% from elsewhere. That would include the, can I please not have that here, Eileen?
No, I'm taking it.
Thank you. Elsewhere, and that probably is New Zealand, Australia, etc. Further on logistics, you should be seeing on the upper right of your screen a little webinar control panel. There's a couple of items to note about that. By default, that little control panel will self-minimize after a few minutes. If you need to get at it, click the little arrow and it will re-maximize itself. Maximize that and note the raised hand icon and the questions box. After each presenter will open up for comments and questions. If you have a message for the presenter when you are recognized by Jerry as the MC, we will unmute your microphone and recognize you, and you'll be able to ask your question. Both the presenter and the audience will hear that. If by chance you do not have a mic, yes, see, somebody's already raising their hand. If you don't have a microphone, you can type your question into the questions box, and Wayne will be watching those, and he will read the questions to the presenter and the audience. If it turns out there's more discussion on an individual presentation than we have time for before we move on to the next speaker, we will have an answer to that. We'll be having an after-hours reception for further discussions after the conclusion of this symposium. If you look carefully at that webinar control panel, you will also find a handouts tab. It's about halfway down on mine. In there is an invitation to that after hours reception. That'll be handled on Zoom. Everybody come, live mics, live webcams, and I have no idea how we do crowd control, but it will be a freewheeling kind of anything goes sort of discussion there. Also in the handouts tab are the papers that go with today's talks, the AAVSO Code of Conduct for Meetings, and a special discount offer from our generous sponsor, DC3 Dreams. Thank you to Bob and Stephanie Denny. This, as I mentioned, is a joint meeting of two great organizations, the Society for Astronomical Sciences and the American Association of Variable Star Observers, which, if you are one of the few people in attendance who are not familiar with both of those, I encourage you to check out both websites to learn about what the organizations do and the assets and services that they make available to their members and to the wider community of small telescope astronomical researchers. This marks the first SAS symposium in decades, maybe forever, that we don't have Earl Wilson with us. Earl died last November. He was a longtime member of SAS, always arrived early to help us get the conference room set up, photograph the activities, was a general cheering presence throughout the activities. He was also an important member of the Riverside Telescope Makers Convention and the China Lake Astronomical Society, and he was a good friend to many members in the Southern California and Arizona astronomy communities. So farewell, Earl. As you go among the imperishable stars, you will be missed by the people you've left behind. I'd like to introduce the SAS board, who keep things going behind the scenes, sometimes in front of the scenes. This is an opportunity for me to show off my new observatory. Bob Stevens is our treasurer and the prime mover and advisor as part of the glue that holds SAS together. Those of you who are in business, you know the value of having a CFO who is engaged in all aspects of the enterprise. And Bob is just exactly the fellow that you want in that position. Bob Gill normally handles the audiovisual at the in-person symposia, and Jerry Foote normally acts as our master of ceremonies. He's also our liaison to sponsors and vendors. This year, both of them are continuing in those roles, albeit in a virtual mode as members of the online production team, which, by the way, has turned out to be a real test of whether we old dogs can learn new tricks. Beware, Jerry still wields the hook, so as presenters are reaching the end of their allotted time, he'll let them know the 5-minute warning. Wayne Green is also on the production team for this online symposium. He worked us through quite a few contingency plans for what might go wrong. That was helped by his enthusiastic willingness to experiment with anything, undaunted by high voltage or other grave consequences. John Mackey has been a fine advisor during our planning and deliberations leading up to this symposium. And John Martin, an energetic supporter of SAS, an important advisor to us on both science and business. Among other things, John has volunteered to handle the editor's job for the proceedings this year. I hope he doesn't regret that. We also benefit from the advice and counsel of our advisors, Arnie Hendon, who I believe is in attendance today and who you'll be hearing from on the 21st. Alan Harris, who's probably disappointed that we don't have any asteroid papers this year. And Dirk Terrell, who has helped us out on several eclipsing binary projects over the years. Our sponsors have continued to be loyal and generous to us. DC3 Dreams, Bob and Stephanie Denny, ACP Software runs quite a few observatories for SAS and AAVSO members. As I mentioned, as a special treat for attendees this year, Bob has offered a special discount. Look in the handouts tab of your webinar control panel. Thank you very much for that generosity, Bob. Software Bisque, Sky and Telescope, and Woodland Hills Camera have supported us for a long time. They're continuing in that tradition this year. And I know that all of you enjoy going to the sponsor and vendors room during the live web symposium in order to discuss products and new ideas with our vendors. Optech, observatory operators, Hyperion Astronomy, Planewave Instruments, and Starlight Express. You're not going to be able to chat with them this year, but when it's time to add to your astronomical kit, we encourage you to look at the products and services of these fine companies. I would like to now hand the screen over to Dr. Stella Kafka, the Executive Director of the AAVSO, to offer her welcome. So, Mr. Gill, if you can make that happen and give her mouse and keyboard control. And do I need to make sure that her camera is live? I will turn mine off.
Wonderful. Thank you, Bob. I am actually delighted to be here. I'm adding my welcome to the symposium and thank you all for joining us. 166 attendees. I think that we are breaking a record this year. In a time where almost everyone is separated, it is really important that we take steps to create a sense of togetherness. And this meeting is exactly an excellent way to bring our community together and discuss topics of our interest. So I would like to start my brief presentation by introducing the leadership team at the AAVSO. These are individuals who are working behind the scenes to run the organization, members of our community, and people who consist our board. These are our officers: Gordon Myers, who is our president; Bill Stein, the first VP; Richard Berry, the second VP; Bob Stevens, the treasurer, who is also the treasurer of SAS, so we're sharing expertise here; Chris Larson, our secretary, and the members of our board: Bob Buckheim, Brad Vigi, Michael Cook, Kent Hudson, Joyce Guzik, Dave Caldwell, Greg Sivankov, and Bob Massey. So if we were in person, I would actually encourage you to talk to them and ask about what's happening at the AAVSO right now, but we're not. So I will try to give you a preview myself here. I'm pretty sure that they're attending, the attendees here. So this pandemic has had affected all aspects of our lives, and it is testing social and economic resilience. At the AAVSO, we had to adjust really quickly to the new reality of social distancing, working from home, follow state guidelines, and try to be safe. We also always keep in mind our mission and that we serve an international community. We managed to continue our work uninterrupted and add a couple of new services in our repertoire. So it's a pleasure to give you a short update of some of the work that we have been doing during this time period. And I would like to start with choice courses. We always offered choice courses that were serving the community, but this year we're actually offering them for free. We aim at reaching as many people as possible who would like to sharpen their skills and enable to participate in observing and research projects through our tools and through observing programs. With the generous cooperation of our choice course instructors, we even increased the class number of attendees to 40 participants for some of the courses, and we've had an overwhelming response to the point where classes were filled within 2 or 3 days of announcement, and they had a long waiting list. Right now, we have a choice course that is actually running with 51 attendees, how to use VSTAR. Jody Baker-Maloney, who is the instructor, decided that she's going to enable anyone who was in the waiting list to actually enter the course. But there are other choice courses coming up. Check the schedule, please, and join the one that you feel that would actually help you move forward or push forward the limits of your observing or your abilities. We also created a group of data mining projects. You know, it's not only social distancing that prevents people from traveling to their observatories. There are also challenges for those of us who live in urban areas, like pollution or bad weather, that we can't actually go out and observe. So we want to give opportunities of engagement with science from home to individuals who just can't access a telescope and they don't have a way of getting their own data, or they want to complement their own data with other data sets. And we created a group of data mining projects and enabling anyone to participate in cutting edge research from the comfort of your home. All you need in principle is a computer and patience. This is the first series of AAVSO data mining activities focusing on unveiling unknown properties of suspected variable stars in VSX. I hope you will take advantage of this, and I'm looking forward to seeing some of the outcomes of those projects published at the Journal of the AAVSO. Of course, we continue our work improving our scientific and operational activities. We are continuously updating VSX. We are responding to your e-questions and provide help and feedback through our help desk. Right now, we have more than 41 million data points in our photometry database, and we are continuing our efforts of data quality checks, especially for new observers. We have more than 3,000 validated spectra in our spectroscopy database. We're working close with our observing section leaders to improve the observing sections and serve you, our community, better through them. And on the back end, we continue our web migration project of Drupal 7 to 8. We're actually improving our infrastructure and we're supporting our databases, always keeping an eye on implementing best practices for cybersecurity. And while we're talking about cybersecurity, we worked with there we are, click. We worked with a lawyer to improve best practices and finalize our data privacy policies. At the AAVSO, we take your privacy really seriously. Those policies inform how we collect, use, share, and protect your personal information. We only share information to comply with laws, to provide you with services, to protect your rights, or to fulfill business obligations, such as science. If you're interested in more details, please go to our page and read the relevant document. These policies are going to be updated as necessary so that we can stay compliant with relevant international and US laws. And last but not least, 2020 is a very special year. We are continuing a strategic planning process with the help of our Harvard Business School partners and deciding on the AVSO's long-term sustainable future as part of our strategic planning. Of course, we wouldn't be able to do that if to offer you all those services if we didn't have our volunteers. We're really very grateful to the group of individuals who are continuously working with us at headquarters and in various aspects of our operation and our science. These are dedicated people who are enrich the AVSO with their experience, their knowledge, and they're helping us improve as an organization. It would be impossible to have all those expertise in place at headquarters. So I'm talking about individuals who are involved pretty much everywhere at the AVSO. Other than our observers who are enriching our databases, our boards and our board members and our committees are volunteers, individuals who work on special projects with us, our VSX team, observing sections, charts and sequences, data validation, our mentor program, our mentors are volunteers. Choice course instructors, software development and support. We have a group of people who are improving tools such as VFOD, VSTAR, and VSX on the back end. AVSO.net, our high-level digitization special archival projects individuals and our translators. And actually, I would like to give a very special shout out to the volunteers of the SAS production team who are working behind the scenes to bring you this virtual meeting. Jerry Foote, Bob Gill, Wayne Green, Bob Buckheim. So where are we going with that? A preview of what's coming up. Mark your calendars. We will start this Saturday, June 20th. As part of this symposium, our president is going to discuss our work and progress with our strategic planning process. Really, you don't have to be a member to attend. So please join us and participate in the conversation. It's going to be a very interesting presentation and discussion that will follow up. We are also, maybe. We will be holding an observing section science fair starting at the end of June. Stay tuned for more information, which will be coming soon. And we are going to hold an AVSO annual meeting, but it's going to be virtual this time. As part of that meeting, we're offering 2 different workshops, a spectroscopy workshop and a data mining workshop. Mark your calendars, November 4 to 8, more information to follow actually quite soon. You know, this SAS-AAVSO Joint Symposium is the first of its kind for our community in an era of social distancing. Digital technology has transformed our sense of time and space, and it's showcasing that we can still be connected across time zones, across hemispheres, and across countries and cultures. We are all working at the AAVSO and the SAS. We're empowered knowing that we are a community of people who love astronomy and enjoy observing the stars, and we can share this excitement online, even at a time of social distancing. We're not isolated. At the AAVSO, we'll continue offering guidance, training, and help you can rely on during this time and always. But for now, from my computer to yours, enjoy the meeting and stay safe. Thank you.
Thank you, Stella. We're about ready to start the whole technical stocks for this meeting. We're going to start off with John Hoot presenting Gaia data enabling new methods of analysis and discovery. John?
All right. Well, my screen's settling down eventually, I guess. Just less than 100 years ago, Edwin Hubble, with the discovery of a variable star in Andromeda, changed our place in the universe. He put to rest the notion that those spiral nebulae lay inside our own galaxy and expanded the universe wherein we were one galaxy out of many. In the ensuing near 100 years, cosmology has received a great deal of attention and advanced greatly. Let's see if the slides will. These do take some time. Come on. There we go. Well, at the same time as the United States was pursuing satellite observing with projects like the Hubble Space Telescope, Europe has taken a different direction. Rather than trying to perhaps establish better our place in the universe, they look closer to home at measuring our place in our own galaxy. First with the Tycho-Hipparcos mission, and currently with the Gaia mission, which has very ambitious objectives, which it has already met and in fact surpassed. It wanted to measure the position of about 1 billion stars in our galaxy and other members of the local group with an accuracy of 24 micro arcseconds positionally. Perform spectral and photometric analysis of all sources, derive velocity of the galaxy's constituent stars using stellar distances and motions to create a three-dimensional structural map of our own galaxy. The satellite itself launched in December of 2019 and has had an extension now out through 2020. It in fact orbits out at the L2 point. I'll get into more of that later. It contains 2 identical telescopes and a radial velocity spectrometer. And it is run by the European Space Agency, and the data analysis is done by a consortium of universities and science facilities throughout Europe. So here's a look at the satellite itself. On the right, you see there's a large deployable sun skirt that faces back towards the Earth and Sun and shields the instrumentation. On that backside is, in fact, a steered phase array antenna. Because they couldn't use a mechanically steerable antenna, it would cause too much vibration and render the satellite useless for its purpose. It sends back a continuous stream at 8 megabits per second to a network of ground stations around the world run by ESA, collecting raw data from the satellite. Above the skirt, you will see a what's called the spacecraft bus. It's the electronics, attitude control, propellant, electrical management system, and so forth. And then above that, there's that octagonal ring, which is actually a giant optical bench toroid. Let's see. So here's a look at the instrumentation package in the satellite. It has 2 telescopes, identical. These optics are folded and refolded again. There are, I think, 4 or 5 relay mirrors in here, and brings those 2 half-meter square panels together on a common focal plane. And the box in the lower right-hand corner contains the focal plane array with 106 CCD detectors. The spacecraft rotates around its central axis at a constant and very carefully controlled rate, and uses time delay integration in order to do its imaging. We call that drift scanning when you do that terrestrially, but they're moving their platform to accomplish the same thing. So here's what the detector array works like. So essentially, at the rate of rotation, this array of CCDs are clocked such that the target moves well, in this dimension, a column at a time across the array in synchrony with the rate of rotation of the satellite. Now, depending on how many of those cells in the array you allow integration to travel through before you read it out, it gives you a large dynamic range. This can detect sources accurately from magnitude 3 down to magnitude 20. And from left to right, they are allocated to special purposes. The left-hand column is used for housekeeping, general pointing and attitude control feedback. The next pair of columns is used for general sky mapping, setting frame of reference. This is a self-calibrating satellite. I don't have time to go into all of that, but it is a departure from previous astrometric missions in that it uses the entire sky to create the reference frame. The next field, the largest field, is the astrometry field. And that's what gets you down to these 26 micro arcsecond kinds of resolutions. clocking through there. And of course, being the largest array, it is the most sensitive array. It's the one that goes down to magnitude 20. It's followed by 2 columns of CCDs. These are the photometric, it's blue, what's called blue band and red band subband, so that we can do photometry and compute effective temperature. Finally, there is a complex spectrograph, very narrow band that uses that 12 CCD array on the right-hand side. And here we see the pass bands and the effective pass bands. The blue line, heavy blue line, that's what they call the blue filter. It's split at roughly 650 nanometers. It splits the band in half. The red pass band is shown, and it goes out into the near infrared. The fainter lines below are those filter responses convolved with the CCD responses, and that's the actual instrumental response in those 2 particular bands. The green line is the total pass band. It's also known as the Gaia pass band, and that is completely, well, it's essentially unfiltered, and it is what the astrometric references are made with. The spectrograph looks at that window that you see outlined in purple, and it covers from about 845 to 875 nanometers. So it's a very narrow band, but that band was selected specifically because it contains the calcium triplet. You can see in the upper right panel there the very sharp lines of that calcium triplet that it straddles, and those are what are used in the satellite to compute radial velocity on targets. But it has some other benefits. There was an alternate band considered earlier in the design, but you'll notice it also has iron lines, silicon, and hydrogen, a helium line, and iron lines. And this allows it to, in addition to doing radial velocity measurements, make some metallicity measurements and some compositional measurement of all of the stars that it targets. Now, the orbit of the satellite is out at the Earth, Moon versus Sun L2 point, which is has a radius of 1.5 million kilometers, making a total diameter for parallax purposes of 3 million kilometer baselines. And that's how you get the really accurate parallax that the satellite produces, which gives us the distance to the stars in the galaxy that it can resolve. So this thing has been spinning up there since early 2014, continuously imaging the sky with this 8 megabit per second hose of data. And the processing is way too complex to go into in this particular presentation and for my purposes, but it has been the topic of at least 3 special issues of the Astronomy and Astrophysics Journal, to give you an idea of the complexity of the problem that they're solved. And you can see that they've divided up the work into different subgroups of this data processing and analysis consortium, which is DPAC. And it's an impressive, it's a phenomenally impressive operation, and has been tremendously successful. I should mention, I forgot in the previous slide, all right, this mission is also revolutionary, at least from the academics' point of view, in that there is no data embargo. That means that as soon as that data comes down, it is available to the public, both the raw data and the data releases. There's no principal investigator who gets 6 months or 12 months or whatever to write their paper. And as a result of that, the science began almost immediately after the data came down, and it's been phenomenal. And you look at the totals here, it has measured, excluding solar system targets. By the way, it also does astrometry for, minor planets and so forth. almost 1.7 billion stars and sources measured. All right. For 5 parameter, that's where we talk about position, parallax, and proper motion. 1.3 billion stars measured. 2 parameter astrometry, position only, 361,000. Linked to the radio, it's created a new frame of reference, ICRF3, and it's cross-linked with radio reference data on quasars, and it's to a higher degree of accuracy than ever we've had before. In terms of photometry, it's G-band photometry, luminescence, and allows us to do stellar mass exactly, or near exactly, with all those 1.7 billion stars. 2-band photometry on 1.3, almost 1.4 billion stars. Radial velocities to date, or at least the second data release here, 7 million radial velocities. It is classified as variable 550,000 sources. That there's something for the VSX folks to deal with. And the variable estimated or variable type, about 360,000 types have been assigned, but they're subject to vetting, something for the amateurs here to do. And detailed light curves of 390 sources, effective temperatures 1.6 billion or 161 million, and so on. It's just a phenomenal catalog. It dwarfs most any other catalog you can think of in terms of its size and relative completeness. And here's an example of what you can do with the data set. This is not a photograph. This is not something somebody ginned up. This is a plot of 1.4 billion sources in the neighborhood of our galaxy, for which we have exact photometric brightnesses in red and blue. So this particular plot, what happened? Am I all right? I hope I'm back. Somebody's been playing the mute button on me. So this is 1.4 billion points plotted. Neither of my screen nor yours, nor any screen, including the jumbotrons I can think of, are capable of plotting all of these. But that's the level of
Hey, John, I think you accidentally muted yourself.
All right. Am I live now, Bob?
Yes.
Thank you. So if you want to get some data here, and you happen to have a large server farm and a big computer, you can download the whole thing from the Gaia archives in Strasbourg. But for the rest of us, there are probably some better ways to
I can't explain it, John, but it happened again.
All right.
Better.
Okay. So those of you familiar with CDS and Vizier, that provides access to the Gaia catalog interactively through a web page. Gaia's catalog is the basic astrometric data and proper motion data in the first catalog, and then a series of subcatalogs based on the source characteristics, radial velocities, variables of various types, solar system objects, and so on. To query, I see what's happening.
It's the space bar.
Yeah, I was using that to advance slides, but I have to be on that screen. There we go. Now things are better. All right. And so this is the query form that you use in Vizier. If you're familiar with Vizier, I'm sorry to be boring you, but you can select the fields you want. You can also constrain the fields, for example, ranges of right ascension or declination or proper motion or parallax. And then click which fields you want and then request as many, a fixed number or as many as you want of the objects to be retrieved from the catalog and the format you wish to receive it in, whether that's HTML or a comma separated value or many other database formats in which you can download the table. It's a good interface, and it's one that's familiar, but it has limitations in how you can query the data. And so if that isn't enough capability for you, it's time to move up to the next tool. And this is called TopCat. It was produced by the University of Bristol in the United Kingdom. And it uses concepts that are familiar to data miners, but may or may not be familiar to you. It's called a virtual observatory cone search or a table access protocol astronomical data query language interface, and it includes graphical visualizations. It's written in Java. It's available on Windows, Linux, and Mac. And the idea is to push the search back onto the servers. So you provide the search query structure to a database server, and it retrieves for you a table which you can then subsequently, in the cone search concept, refine subtables of that table to work with. I'm going to run through a quick example here of M45. So I go a cone search, I select a server, I've done a keyword search on Gaia data release 2, I pick a table server, and then at the bottom I key in, I'm interested in finding information related to M45. It gives me the coordinates. I say I want to look at a radius of 3 degrees around M45. When I get that, I plot the proper motions in RA versus DEC in a scatter plot here. And you'll see that there are two concentrations. The large one in the upper left is most likely our motion relative to the galaxy as a whole. But the one on the bottom is probably those co-moving stars from M45. So you graphically draw an ellipse, or you can do a polygon, squares, a number of ways you can select spatially and graphically what you want. You say, all right, I'm interested in then that subset. And it then winnows down and creates a subtable from the primary table, which I, in this case, would call co-movers. And then subsequently, I take the co-movers and I plot them in a histogram against parallax. And I pick those co-movers within a few tenths of a milliarcsecond per year of the common mode, and say, I'll bet those are all M45 members. All right. And then I do a sky plot, and you realize that the M45 is a much larger cluster than you probably ever realized. I certainly didn't realize it was this far extended. And if you look on the right, I've, for grins, thrown a histogram of the 800 odd members that I selected this way. And the Pleiades that we see visibly are those little 2 bars on the left there. But you can see that the absolute magnitude of the stars in the Pleiades go way out. The size mass range of the stars produced in that cluster is quite large a spread. And just for fun, after that, I threw together an HR diagram by plotting the B magnitude minus the R magnitude against the inverse, the arithmetic inverse of the G-band photometry, and voila. There you have the fastest HR diagram I've ever produced in my life. So that's the kind of power in cone searching, and that's really good for looking at this kind of a data set, but only this kind of a data set. The next step up in the game is called Astronomical Query Language, and it's a SQL subset. It's a common language used in data processing, and they've extended it with geometric concepts. So it has notions like, you know, all of your trigonometric functions, and is within a radius of, and some of these other concepts which you don't normally find in a relational database. And the way it works is you write a query, and here are a couple of quick queries. But the things that it lets you do that is harder to do in a cone search is you can then link multiple tables. So in this case, as a preview of my next talk, I've gone and said, I'm looking for the stars that are in both the MG1 catalog and the Gaia RR Lyrae variables, and create me a new table that merges those elements that are common to both of them, and then select specific fields that make that table. And then the additional power of the table query access method is that you can then upload your table, your newly created table, to the server and continue the process iteratively, merging sources and data from multiple catalogs, and then you're getting into the serious data mining. So this is the tool that really hammers the job. So ultimately, astronomy is still an observational science. Even if you have to build a satellite, you still can't go out there and put 2 neutron stars on a collision course and say, now let's see what happened when they rack together. You have to go out and find where the physics or the phenomena you're looking for is happening to create your observational program. And that's where Gaia is going to change the game for us. Here's an opportunity to winnow that search down for the targets that you're specifically interested in the questions that you want to answer. And I just threw a bunch of ideas up against the wall here. Some of them stick, some of them won't. But some of the things that this will allow us to do, you know, use white dwarfs to determine the history of star formation. They all cool at a relatively constant rate. Now we know where a whole bunch of them are. You can go out and find them and see what they tell us about the rate at which stars die as opposed to being born, but there's a relationship there that's clear. Spectroscopic binaries about their differences in their chemistry. Are some of these chance orbital pairings, or are these all formed in a common space? Again, we have the tools and the data to go chase that. For double star viewers, life just got a lot easier. Is this a double or is this a binary? You gonna pull the hook?
Pretty close.
Okay, all right. I won't go through all of these, but one of my current projects is to turn Wilson-Diviney inside out. Now that you have parallax, you should be able to compute radial velocities and solve binary star systems without spectroscopy. That's one of my toys for the maybe next year, whatever. Stellar seismology, lots of fun stuff. So here's some of the resources that you can use to start digging into it, and have at it.
We have just a minute. John, I assume all of these references are in your paper?
Yes.
Which is downloadable. There's a link to it on the on your website, or on our website.
Right. And I assume that a copy of this will be available too.
Yes. I've got a question from, I cannot pronounce his name, Yazes Kumar. I've opened your mic. Say again. Hello? Well, let's come back to that. Any other questions for John? All right. Thank you very much.
Well, thank you.
We're going to take about a 5-minute break here, so that should put us back here at about 55 minutes after the hour.
Hello, everyone.
Hey, Stella.
Nice. I'm not going to share my camera simply because I want to leave the bandwidth for others. That was a really cool talk.
Yeah, you know, it resonates with the data mining workshop planned for November, I think.
Oh, yeah. There are lots of ideas on data mining. There's so much data. It's what we were saying all along, right? There's so much data out there, and still they're incomplete. Wonderful.
Mr. Cumrucho Miller, I hope I'm not bungling your name too badly. If you're still on, can you try again with your microphone, please? I see the system saying it's hearing noise, but I'm not actually getting audio from you. No, I'm sorry, that's not working. Probably the best thing then is to see if you can type your question in, and we'll pick it up after the break. Hey, Jerry, did you invent the countdown timer?
Nope, that's not me. I think that might be Bob Gill.
Oh, very cool.
It's very strange to give a presentation with no audience feedback.
Yeah. Well, I think it went great.
We were all clapping, John.
Well, at least tomatoes don't come through the screen.
Hey, John, this is Wayne. Unfortunately, I was one of the ones that I muted you once because there was a lot of background noise, and it turned out there was somebody in the audience somehow had a microphone on. And when I muted the audience, I killed everybody.
Whoa, okay. Yeah, all of a sudden this voice starts saying, mute, unmute, mute, unmute. And I'm looking over at I've got a double screen system, and I'm looking over the corner going, what's going on?
Yeah, Wayne, the system is supposed to automatically mute all attendees.
It could well have been some of us. I don't know.
No, I checked our board and we were all muted, except for you.
Panelists, I mean, unless you actively mute them, are not muted. And so we had a few people that were unmuted when we started that talk, and I had put some stuff in the chat, but I'm glad somebody took care of it.
Yeah. Yeah, I try to mute myself that way. I won't be the offender.
Okay, Tony looks like he's muted. Let's see if we can find him somewhere. I got like 18 screens up here. Oh, here he is, staff.
Oh yeah, I'll unmute him. There you go, Tony.
Yep, thank you very much, guys.
Wayne, Wayne, for your info, the person who had their hand raised, I unmuted his mic and it still didn't come through. I could hear noise, but no speaking. So I advised him to try typing a question. So you might see if it's in there.
Yeah.
No question. Does anyone know when Gaia DR3 release is scheduled?
That
I
sounds
think
like a
it's
question.
October.
But it's subject to vetting.
Yeah. See, I think it was originally scheduled for October.
And I know that DPAC has suffered tremendously under corona stress in some of its sites, and I suspect it'll be pushed back further.
Yeah, so I'm going to answer that it's October and that COVID will probably set it back. It looks like we're down to online again, guys.
Yep. Ready to go.
Okay, I will close the cameras on John and Tony and me and Stella.
You can
Okay.
advance it one, Bob. I just had bumper slides in there to make sure.
Okay, you should be up.
Okay, let's try it to see if it works.
Next, we're going to share from John Martin, Beyond the Milky Way, Comparison Stars for Photometry in M31 and M33. John, cheers.
Thank you, Jerry. Okay. First, thanks for coming, guys. Let me just introduce myself just quickly. I'm John Martin. I'm the Observatory Director and Associate Professor of Astronomy and Physics at the University of Illinois Springfield. And I want to thank some of the supporters of this work to start with. This work was actually started under a National Science Foundation grant going back in 2012. It continues to be supported by an endowment at the University of Illinois Springfield for the observatory. I want to also thank my collaborators, and in particular, I want to thank, next slide. I'm probably going to get it going 2 or 3, aren't I? Yeah, okay, there we go. Particularly, I want to thank the volunteers at the Henry Barber Observatory, because we are an unusual academic observatory in that we are run by community volunteers. We have no graduate program. We do not have an undergraduate degree in astronomy even, and these are the community members who have helped with the imaging for the survey and some of the work I'm presenting today. So I want to acknowledge that. Okay, so the high luminosity part of the Hertzsprung-Russell diagram is kind of a tangled overlap of evolutionary tracks and classifications. And in this part of the HR diagram, we have limits that are both known physics and unknown physics. Okay? This includes a lot of interesting targets. Jerry would need to get out the hook if I was going to talk about all the interesting targets up here today, but suffice it to say, lots of interesting targets. And they're also known to do interesting and exciting things. I mean, think supernova and giant eruptions. And so these are really interesting stars and really interesting variable stars to monitor when it comes down to it. So the best place to actually observe these are in the 2 nearby spirals in the local group, the Andromeda Galaxy M31 and the Triangulum Galaxy M33. And the reason why these 2 places are really the best places to observe the most luminous stars are that these stars are very massive, they have very short lifetimes, so they don't wander very far away from the star-forming regions which they're birthed in. And in our own galaxy, of course, all those star-forming regions are in the disk, and a lot of them are obscured behind large amounts of dust and gas. And so if you want to study these stars in the optical and the ultraviolet, looking at them in Andromeda and Triangulum are your best bet, because there you've got the whole spiral laid out without the intervening dust getting in the way from you really observing the star-forming regions. Okay? And we have literally dozens of targets that of high luminosity stars in both of these galaxies to study, packed into a few square degrees. Now, one of the issues though with the targets being in these galaxies is these galaxies are both over 2 million light years away. Okay, so that makes the targets fainter. Now, I have here two Hertzsprung-Russell diagrams, one for M31 and one for M33, where I have plotted the absolute magnitude of the star on the left-hand vertical up and down y-axis. Okay, that's the absolute bolometric magnitude. Now, the distance modulus to M31 is about 24, and the distance modulus to M33 is about 25. And so this means if the limiting magnitude of your images or your sky brightness is somewhere around 20th magnitude, that's going to be equivalent in those two galaxies to something that's an absolute magnitude of -4 or -5. That might seem really bright, but when we look at what's available kind of between 14th and 18th magnitude, that encompasses still a large number of these high luminosity stars that can be imaged with ground-based telescopes in these galaxies. They are bright enough to actually image in that range we're used to often dealing with. Okay. So, I guess if you're named John, you need a picture of Hubble's first plate in your talk this year. We'll see if this continues. Not Hubble's first plate, but the one he discovered variable one on. So if we're going to talk about studying stars in M31 and M33, of course, this starts way back at the start of the 20th century, where there was great effort put into resolving and identifying variable stars in these galaxies. And the first person to really successfully identify the variable stars was Edwin Hubble, who used the 100-inch telescope, the 100-inch Hooker telescope in 1924 to discover and identify the first variable stars in M31 and M33. Now, I like to look actually at this exposure here, this plate that Hubble took, because we've all taken images like this. We know that today that wouldn't take us very long. For Hubble, this was sitting at the observer cage on the 100-inch telescope, manually guiding for 40 to 60 minutes. Now, today, with the technology we have auto guiders, first of all, and second of all, we have a much more efficient means of recording the light in our CCDs. And so that means that an image like this plate might take like a half-meter telescope only 5 to 10 minutes now. Okay? In fact, the amount of, okay, there we go. Oh, okay, I'm in a mode where I'm maybe on the right slide, maybe not. 1 second, sorry guys. Okay, so M31 and M33, we can observe this on stars in those galaxies now. These stars that took such large effort to observe at the start of the 20th century can now be observed by off-the-shelf technology. Okay. In 2011, there's this example of a group of non-professionals led by the AAVSO that actually reproduced Hubble's seminal work from the start of the 20th century in their own backyard. And we also know people love to take pretty pictures of these galaxies. So it raises the question, actually, why don't more people do science with their images with these galaxies? Well, one of the reasons for this is a lack of charts and comparison stars. So the AAVSO encourages observation of variable stars by providing finder charts and comparison stars to measure the photometry on your images. Okay? The Variable Star Index, VSX, identifies dozens of targets in M31 and M33. And those and more are shown in green on both of the galaxies here. Now, it turns out in M33 that none of the targets in M33 have comparison star sequences. There are no comparison stars identified for charts in M33. And only 10 of the targets in M31 have comparison star sequences. The comparison stars identified for AAVSO charts here are shown as blue dots on M33 here. And we see if we take an image, and I'm partial to images that are 20 by 20 arc minutes on the side because that's what my telescope does, but that's a relatively large image coverage area. And you see that it's possible to put down and image targets actually that don't have any comparison stars within like 10 arc minutes of them. And that's problematic then. This is a hurdle to doing photometry with your images you might be taking of these galaxies. Now, the AAVSO sequence team since 2009 has done a heroic job of answering the call to come up with charts and comparison sequences for every single target you request of them. And they are a treasure to us all. I'd say a national treasure, but they're a treasure to the world. They do great work. But since we have in these two galaxies a bunch of targets that are basically in the same magnitude range, it would be more efficient for us to identify a list of suitable comparison stars covering all the stars, covering the area of the star forming regions of these two galaxies, and have that be available to people to use as a list that we know you can plug into your image and do good photometry with. Okay, now I'm not doing this well for the good of everyone. It's great to do things for the good of everyone, but the way I came to this to start with was a bit of a selfish motivation, because I was looking at this survey we're doing of luminous stars in M31 and M33 and needing comparison stars to do them. Now, this survey has been going on since 2012. It's done with images that are 20 arc minutes on the side and 4 filters, B, V, R, and I. And to date, in those 8 years, we've taken about 814 images of these two galaxies and those filters. We're covering currently about 214 targets. Those targets range from 14th magnitude to 20th magnitude, most of them between 14 and 18 though. And we've already published one tranche of photometry on this in the referee journals in 2017. And when we did that, we used an old set of comparison stars that we identified using the AAVSO tool Sequoplot. And I have a link down there in the corner for Sequoplot, which is actually the tool that the AAVSO chart team uses to winnow out and find stars for comparison star sequences. Now, using Sequoplot, actually most of the stars that we ended up with in our comparison star list were from the AAVSO photometric all sky survey data release 9. And the reason for that is that APAS, as it's known, actually covers the magnitude range from about 10 to 16. And its goal is to do that kind of in a nice uniform photometrics system over the entire sky. And so it's well suited kind of for this type of imaging of these two galaxies, for targets in this magnitude range, to find comparison stars for that. And so it wasn't surprising that using Sequoplot, we ended up mostly with stars out of that. Now, the comparison stars we had were good before. Our original goal for the survey was to do a photometry that was good and precise enough from year to year to sense large changes in the star's brightnesses, to sense basically large evolutionary changes like Estratus eruptions or supernova imposters. So we were looking at the 0.1 magnitude level, which for most of you guys that do CCD photometry, you will consider god awful, like your worst day ever. We were able to do better than that and play somewhere around 70 millimagnitudes instead of 100 millimagnitudes. And so we thought, playing around with the comparison stars, we ought to be able to get it even better. And having taken a lot of images in this survey, it gave us the opportunity to not just use the APAS catalog, but to combine it with the images we had taken in this survey to really come up with a much better list of comparison stars to use for photometry in fields for these two galaxies. Okay, so to select the new comparison stars, we started with APAS DR10, and that's data release 10. It's been out for about a year. I have the web link there for it on the AAVSO website. And we selected all the APAS DR10 stars that were near to our targets within about 10 arc minutes of them, that had magnitudes in B, V, R, and I. So all 4 magnitudes in the APAS DR10. From that list, we started to narrow it down by setting a bright limit. Stars that are at 12th magnitude or brighter saturate on our images, so they are useless as comparison stars, so we just toss those out. We also took a color cut, and that color cut is following the recommendation of the International Chart working group in 2005, where we take B minus V between 0 and 0.8. That actually helps eliminate a lot of variable stars because it eliminates many late type stars, which might have just irregular variability in them. But it also has the advantage of this color cut of putting that the comparison stars have colors that are similar to the targets we're interested also in these two galaxies. Okay. What we do next is we have this list of stars, then we've taken from DR10 and winnowed down, and we find and calculate their brightnesses in our survey images. We actually find the photometry for them, measure their brightnesses in the 8 years of data we have in images. Okay, and we find their photometry using the old comparison stars initially here. So from the brightness of a star on this list, we can then calculate its average brightness and the standard deviation of its brightness over 8 years. And we can use that to further refine the list of possible comparison stars by requiring that the average brightness we measure in the survey is equivalent to the magnitude that's measured in APAS, and also requiring that the star have a small sigma, very small standard deviation in brightness over the 8 years, again, requiring basically winnowing out stars that might be variable. We set a limit on the standard deviation for the stars at 50 millimagnitudes, which I know is a little higher than is recommended for CCD photometry, but actually in the magnitude range we were working in, if we went to the recommended 20 millimagnitudes, we wouldn't end up with enough stars. So we're going to start with good enough here to start with, and hopefully down the road we can improve this a little more. I'll talk a little more about that later. Okay, so once we have these stars from DR10 that we've taken and we've done quality assurance for in our own survey images, we then test those stars out by using them to do photometric solutions on all the images in our survey. And from those photometric solutions, we get out ensemble 0 points for each image for the photometry. And we can throw out then the stars that are not going to be good comparisons, that are consistently off the 0 point by a lot, to do our last cut and get down to just the very best stars to act as comparison stars for photometry in these galaxies. Now, as a result, after doing all that, we ended up with a list of 317 comparison stars, and those are listed in tables 2 and 4 in the proceedings, and I also have it available as an electronic downloadable online. That is available. I have the URL at the end. There was something that popped up in the corner there. What was that, guys? Distracted me a little. All right, we'll find out later, I guess.
That was your 5-minute warning.
That was my 5-minute warning. Thank you, Jerry. Okay. Now let me keep going here. Okay, so here is the spatial distribution of those stars in the two galaxies, and we see that this is much better than the existing comparison stars available. As we said, in M33 we didn't have any. In M31 they were sparse and patchy. Here this is nice and uniform. It would be very hard to put down an image in one of these galaxies and not get several comparison stars in this list on your image that you could use to do photometry. We've done a couple of checkouts on this list. One way to check it out is to, we can compare the 0 points, the standard deviation of the 0 points in the photometric solutions, and those we can use those to basically judge the errors from the standard deviation in the 0 point from the ensemble photometry. Okay, now we show here histograms of those 0 point errors where for each filter. And we see actually in this case that the 0 points in the photometric solutions on the survey images mostly have an uncertainty of less than 80 millimagnitudes, with over half of the B, V, and R images having a better than 50 millimagnitude precision. I-band is a little worse. Hopefully I'll get a chance to talk about that. There are a couple of reasons for that. And for comparison, the 0 point errors with the old comparison stars are shown as the gray histogram behind. Now, if we go to the numbers here, I have compared the new comparisons with the old comparisons here, And the numbers are the average 0-point error in the solution and the standard deviation of those 0-point errors over all the images. We see actually in this case that the 0 points in the photometric, we see that the numbers for that the new 0-point errors are not significant better than the old. Okay, but there are some exceptions. It turns out that the new comparisons have fewer of these high error exceptional solutions. So that's where the real improvement here is in making the photometric solutions more consistent across all fields. Jury's ready to pull the thing. I'll get here. Okay, another point of more consistency. It turned out that with the old comparisons, that the 0-point error was significantly higher in the M33 fields than the M31 fields. That led to the double peak we see here in the gray histogram for the I solutions here. That double peak was, one peak was M31, the other peak was M33. So in the new solutions, that disappears. We have better consistency across, and I think that's a compliment to APAS actually, that APAS has cleaned up the magnitudes in M33 a lot better. Why don't I just go through, I also have done the errors, the photometric errors for the stars. We see actually that there is an improvement in the brighter stars in B, V, B, R, and I, not much of an improvement in V, okay? We see fewer outliers, that's where most of the improvement comes from. There are larger errors in I, that's due to APAS having larger errors and also fringing on the CCD images, creating basically higher errors in the instrumental. And I think actually at this point, you guys can read most of the rest in the paper, and we want time for questions. And so I'll bring up my last slide here that has the link where you guys can go and download the comparison and checklists that we've developed for these two galaxies. I want to also let you guys know that we submit the photometry for all the targets in our survey that are in the variable star index. That photometry is submitted to the AAVSO International Database. So we invite people to collaborate with us there. You might be taking images at a different cadence than our survey, and you can contribute to what we're doing on the targets there in the international database. You can contribute yourself there, and I encourage you to do that. And I'm happy to take questions if we have them.
I think we have, I've got Jack Martin from, he's from the UK. He has a question.
Of course.
Jack, go ahead. Jack, you're ready to go. You'll unmute your microphone. Nope, apparently not coming through.
Questions aren't working today. I'm happy to, you know, if they put them in chat or whatever, if there's a way to do that, I'm happy to answer the questions that way too.
John, we have a question from the audience. What is the minimum size telescope to measure these stars in M31?
Well, so the size of your aperture would basically just set your exposure time, really, right? We'll say, now here's one of the great things about going after the most luminous stars in these galaxies. They are the brightest, they're the most luminous. And so you're going to be able to pick them out even in crowded fields. Sometimes if you have blurring with other fainter stars behind them, those fainter stars they're blurring with are going to contribute insignificantly to what you're measuring for the really bright and luminous star. And so if you have an 8 to 10 inch aperture, you're probably getting yourself into the range where you can take images that you will be able to resolve these stars individually in, I think.
Okay, we have another question from George Silvas. Will these stars be added to the AAVSO VSD CompStar database?
Well, I am an independent contractor. I'm happy to provide them to them. I will say, George, if you go to, George probably has more of a pull on that than me. George, if you go to the URL I provided there where you can download the data, I have provided them in the SEQ plot format to be loaded into the AAVSO database. So I hope somebody's listening that can do that, that likes what I've done here.
Thank you, John. Appreciate it. Very interesting method you used to get those stars, and very interesting talk. Next, we're going to hear from Wayne Green towards the flux calibration of small telescope spectra.
Start my clock here as well. Tony Rada, Clark Yeager, and myself got interested in what would it take to do flux calibration of these spectra. And what we found was, I'm not advancing my slide here somehow. There we go, maybe not. Okay, can I get the next slide, please? We're a little hung up on the slide mechanism.
I'm working on it.
Okay. Okay, so our goals were to find so-called reference stars, photometric reference stars, spectrophotometric reference stars that we could use. Did a pretty extensive search of the existing library and stumbled across this one, the Next Generation Spectral Library. Because of COVID-19 and the inevitable inclement weather, we didn't get as far with this particular project as we had hoped. We did look at measuring sensor response, which is critical to this this game. And but we're not really spend a lot of time reporting on that. Okay, next to the slide here. My keyboard doesn't seem to be helping me out, guys. Oh, there we go. When we ask about qualified reference stars, we went and said, well, gee, the common white dwarf is your best bet, but they're all pretty dim. So I gave you a distribution to show how John Martin can use some of these guys in 20th magnitude, but it's certainly out of the reach of the small telescope scientist spectrograph. So our common wisdom was sun is pretty bright, white dwarfs are pretty bright, but we also have an awful lot of A05 stars, which have typically narrower features and a smooth continuum. And we also wanted to collect together information on the tellurics. So for the reference catalogs that we looked at miles, e-miles, CalObs, and CalSpec. And these were ones that had been brought up in the 2018 SAS meeting as potentially good reference sources. So we thought, okay, let's go to the original repositories and get these data for ourselves, just to make sure that all of the common DAT files that are floating around are the same. We also found some other catalogs like RAVE. RAVE has a very narrow spectral wavelength that John Hoot mentioned earlier, and that was the ground project that was helped or put in place to help design the spectrograph on Gaia. We also found Elodie, which has some promise as well, according to our logic up to this point. And we kind of thought about maybe Apogee 1 and Apogee 2. So evidently, we're still tantalized here. We're thinking this might be a good avenue to continue exploring. And so what we did then is we went and got Next Generation Spectral Library. Now this was done with Hubble with the Space Telescope imaging spectrograph. So it's above the atmosphere. So there's no atmospheric business that we have to deal with. Also, they did not put their finger on the scale by guessing at extinction between here and the target. So what we see on the ground is what they saw from space. However, it does have our atmosphere into it. And we just have to live with that. The other interesting thing about this is it goes from about 0.2 microns out to just past 1 micron. So that includes the UVA, the really nearby UV that can feed into this new UVEX spectrograph that the folks over in France are working on. The resolution of this catalog is around R1000, fits our needs to a T, has 375 stars, roughly 4 pi sky coverage. So still pretty tantalized here, right? Still, is it perfect? So we jumped in to scrutinize this thing and we said, well, gee, it's a little sparse in the south, but we notice there's an awful lot of observations along the equator. So that means that people from the south can see these things, people from the north can see these things. All right, still encouraged to keep digging. So our next thing is I talked to Anthony Rada. We'll be hearing from him next, I believe. And he gave me his target catalog, which I plotted. Now this plot was made by Simbad, TopCat. TopCat also produced the plot before this. So this gave me an idea where I could sprinkle the stars on the sky and go back and compare that with the previous graph, or merge another catalog in here and see which is near to me, which is a really good reference star to use. Okay, this is looking good. Still keep promising. So Tony went and took a few observations between the infinite number of clouds that he was having. And we got some pretty decent agreement. You'll notice that there's a little bit of a dip down in here, which is probably due to the atmospherics involved. And these major dips in here are definitely water telluric bands. So that means that we have to keep track of those tellurics. So that's still a good goal in our project. He went and took a look at a different star. And I want to call your attention to this little defect here in this area. This is an area that's a glitch in the original Miles data that they just sort of guessed the continuum through here to let us keep going. I'll get to that here in a minute. And then we also took a look for conformance. You can see some pretty deep water features in here. These are the things that began to become interesting to one of my friends that works in atmospheric sciences. Can we use this to make some measurement of atmospherics by doing small telescope spectroscopy of brighter targets from the ground? That's a project that we dealt with in the paper. Here is for HD 185351, I overlaid, or this shows you the complete spectral coverage range. Notice there's good coverage down in the UV, well beyond what we can reach with the atmosphere, and some pretty reasonable stuff as far as our sensors go out towards the IR. And I overlaid this box that shows where Tony's range was for the images that you saw above. Here's where we kind of zoomed in. Remember that little feature that was a straight line up in this area is now filled in. The next generation spectral library has been through 2 or 3 iterations. Miles and so forth use roughly the same data, but they played a few games with it, as will be done with reference stars, something that's not very tantalizing that we'll get to here in a minute. Here's a little zoom in for you guys that are hanging on to spectral references for ultraviolet work. It shows the detail of these features, remember, taken above the atmosphere and so easily available and accessible to our sensors. Our sensors really start getting pretty bad around 3,000, but it goes all the way up to 1.2 microns, so you're in good shape. Next question was, if we're way down in the atmosphere, remember the professionals observed from the mountaintops and we're down in the valleys or literally on the seashore, we decided to take a look at all the spectrum or all the filters that we might use with this. Bessel has a technique where you can take V-band filters and get a pretty good guess of basic flux for a star of a spectra by integrating over that same area in the spectra. So we said, what is the ground doing to us? What are our light pollution? What are our cities doing to us? So Clark Yeager went and put a study together on those filters, and we're pursuing that more into the spectrographic filters, VBNR, the Sloan filters, as well as the narrowband filters. And one of the things that Clark had done is he had taken a look at both an LED bulb as well as one of the electroluminescent panels. And this is a spectrum that he measured with his own equipment that shows response curve for those two devices. And this is actually kind of tantalizing to us again, because it gives us a strong signal in the blue, something that tungsten doesn't do for us very well with the tungsten lamps. Gives us a pretty good idea about how we might go about flux or helping to flux calibrate our own spectra. So is this attractive? You bet. Do we need to dig deeper? Well, turns out you bet. So what I had done is gone up using TopCat, and I had done one of the queries that John had shown you, and I brought down all the Simbad data I could get my hands on, and I course correlated that with the synonyms for the stars, all of the flux calibration, and together with the general data that was there. And I found out that NGSL contains quite a few oddball stars. by Simbad's definition. I also found out that Simbad's object types S, the plural version of that, contains a laundry list of potential classifications for these stars that don't necessarily make some sense. For example, I found spectrographic binary stars that were not indicated as being double stars. Well, we know they are. So you have to be kind of careful. You have to have a more complex logic in order to winnow down the constraints for each of these target stars. And that's where things started getting a little bit more interesting. Once we had our hands on the data in a database, local database, we were able to do quite a few queries of those things. So the characters of the NGSL data is that for stars less than 10th magnitude, and really that's about a lower limit of magnitude for us to work with a small telescope and with the small spectrographs. We found out that 6 of them were BE stars. A lot of them are the same kind of stars that we want to be measuring to begin with. And in other words, highly variable. Across the whole catalog, we found that there were like 50 different types of classifications for the 377 stars that we brought down. I gotta be a little bit careful. 2 of those stars are actually the sun. So when we looked at the Hubble Space Telescope constraints that were added, that's a really good thing. No telluric lines, no atmosphere, because we're above the atmosphere for the contributions that our air would kick in. However, they did the wavelength calibration by using features that were in the star's photosphere. So that means that the spectral classifications are in the star's local frame of rest. Turns out to be kind of good because it pulls out both the orbital speed of the satellite, Earth rotation, daily rotation, as well as Earth's yearly rotational speeds. So these are just something that we have to hold in the back of our mind. We have to slide the energy in the NGSL spectra a little bit to match our local observation to get a more precise calibration. We looked at things like parallax, proper motion, and radial velocity. Well, it turns out that Simbad also offers you bib codes. Now, up until this project, I kind of ignored them. But this time I found out, because I was able to search and count them, that most of the data, the Gaia data that was included in Simbad's data came from Gaia Data Release 1. In other words, 290 of them were referenced in this one paper. The rest came from Hipparcos, or kind of spread around in various other places, or maybe come from a slightly different paper. So we wanted to use Gaia DR2. So to get there, we went through this TAP protocol via the Astronomical Research Institute's Gaia database, one of my favorite places to go. So here's an example of the queries that we did, where we just simply said contains the point, which is one of our 275 stars. Remember, 2 of them are the sun. And we said we wanted to Gaia tell us about all stars that are pretty close to the ones in our catalog. And it turns out, I chose 0.001, that's about 3 arc seconds. So one of the things that we had that gave us a little bit of grief was we took these FITS headers, were older headers. They were written at an institution that had their own philosophy about writing them. They used multiple data headers. They used older files. Keywords were different. Star names weren't exactly right. Sometimes the star names are spelled goofy. And so what we decided to do was to not try to make them look like us, but just to assimilate their headers into our database as this JSON-B format, and that's a key value pair. And for the value, what I did is I went ahead and merged the actual numeric value with any comment that was there. So I retained as much information from the header as possible. We can set up some database, Postgres database tricks on our end. So we saved our tables with a raw underscore prefix as all incoming data comes in that way. And then we can change it over to the way that we like to look at things. So now to continue augmenting this thing, TopCat and Simbad and Vizier to the rescue. If you play around with Aladdin or Simbad or Vizier, you'll find there's about 20,000 catalogs you can pick from out there. Well, we didn't need that many, but a lot of times some data comes in sex-adjustable format. So we wrote a couple of custom scripts that we embed in our database as an external library. And I call it sex-adjustable to RA, sex-adjustable to declination. Things like star names and things, you just have to resolve by hand. Fortunately, there are a few of them. Given the coordinates, Simbad queries, you can work it down. Like if it comes up with something really dim, you know that wasn't the star, but the bright one probably was. So in order to get around matching up the RAs and DEX, there's a fellow out there, Sergei Kospazov, who has a Q3C indexing scheme that we can add to the Postgres database. It's part of a GitHub, the reference is in the paper. And that permits our own local version of co-matching coordinates within our database. Some of this material has been covered, so we may zip through some of it here, if I can get the button to work. Come on, come on. All right, did things mess up again for me? Yes, I'm wedged. If I can back up, go forward. Okay. Mr. Gill, up there we go. TopCat was covered in the previous discussion by Mr. Hoot, so we'll kind of gloss over that. One thing I want to point out is TopCat has a Java database connection package that ties directly into Simbad. That means I can take the table down from the cloud, do a few manipulations on it, and store it directly into my Postgres database. I can also query my Postgres database to get a local table. Let's say I bring up the main ID, the RA, and the DEC, and then using this tap upload scheme, I can use that to do joins on the data. One other little problem that comes back is TopCat occasionally brings back one of these null characters that trips up the JDBC interface. So we just take a quick side trip. I use Unix or Linux through Linux, cleans the table right up, and we're back into it. I can then create the table directly. I can do an insert select. I can use materialized views. I can do lots of tricks. Just for completeness sake, here's an example of one of our queries. It's in the slides, so you guys can refer to that later on. Okay, so it comes down to finding the reference spectra. We just did Google searches. And pretty soon you hold your tongue right, you find that they come up with a list of the actual locations in the cloud that you can download the raw FITS files. It takes a little bit of work, but not too much. If you're handy with an editor, it gets done pretty quickly. And then we used pretty much Anaconda Python to convert these FITS data down into the typical .dat files that go into programs like ISIS and Demetra, things along those lines. So now let's start getting our stuff into a bucket. Well, a bucket in our case is a Docker container. By putting the database engine and whatever else we want in a couple different configurations, we can move these containers around in such a way that I can tear it down, put it back up again. If it gets corrupted, I can just easily backspace. It takes like 2 minutes to get another container running to kind of take care of the mistakes that I just made. I can put the data stored within my container. I can have it external. Or what I can do is I can really load up that Docker container with things like Nginx, which is a web server. I can throw in extra programs like the programs I use to data scrape and clean. Okay. The architecture is set up so that each of these PSQL clients can be, say, something that you've embedded in your own Python code. It can be done through a manual interface. There's even a way that you can hook Excel up to Postgres. We can also bring in some external telemetry, for example, and combine that with the data as we collect it. Kind of go through, there was the important slide. When we were in things, we noticed something. We noticed that a lot of these data, like you saw up in Tony's slides, didn't quite line up. And so that means the conclusion that we've come to is that we have to collect our own data together and we have to qualify them exactly to our own needs. So what does reference really mean? It really means stellar modeling. It doesn't mean spectrophotometry. So in summary, what I'd like to say is that this is a little workflow. We used TopCat to bring data in. We found the original data. We did our own little Python program to produce these raw files into Postgres. We used tricks of various kinds to convert the raw into what we wanted. And now we become interactive with TopCat, which again folds back into the major libraries and data repositories that we can do. So to publish a lot of stuff, that what we're going to do is put things out on GitHub and put things out and read the docs. That material's out there, and it's referenced in the paper. But I particularly would like to thank these guys for providing a really nice access to the DR2 data, and also to the hordes of open source developers. Everything that I'm using under Linux, and it was free to me or for any of my students. So with that, we'll conclude my presentation, and I'll take questions. And I seem to have a lot of questions. Let's see if I can read some of these. Since I see the questions, I can do some of them.
Wayne, I'll be happy to help you out.
Go for it.
Wonderful news. It appears that the SpaceX Falcon with 2 astronauts on board has successfully launched.
Yes.
And Pradeep Karmakar has 2 questions. Which software is to be used to reduce this type of spectra from raw data, and how do we get the raw data and the relevant software?
Well, no presentation will be complete without me using the 4-letter word IRAF. And I can use other 4-letter words like ISIS, 5-letter word like RSpec, some odd number of word Demetra, and there are several other packages out there that are readily available. Take your data by whatever means that you do. John Hoot had turned me on to the Odroid that's mentioned in Tony's talk coming up as a way of actually managing the equipment up on the telescope. And then once it turns into a FITS file, you can do lots of things with it. As far as our data is concerned, we're making it available probably a little bit later in the month because COVID kind of moved our timetable up a little bit. As PG dumps of data that way, the .dat files will be available for you all in a GitHub repository that's publicly accessible.
I don't see any hands raised.
That's a good thing.
But I have a question.
Yes, Bob?
You mentioned that the spectral wavelengths for the NGSL are in star rest wavelengths rather than our observed rest wavelength. I'm guessing for those of us who use ALPES or LISA, R of 1,000 or thereabouts, unless you have a really pathological high radial velocity star, that's probably not an issue for us. Am I thinking that correctly?
Pretty much. At R1000, at R5000, something like 70 kilometers a second is a pixel. And so in a lot of ways, these data are pretty much easily, readily usable by us. The one thing I'm really looking out for are stars that have high radial velocities in the sky to begin with. And those would be ones that we would definitely want to pay attention to. Remember, I mentioned these stars were for modelers and they're not for spectrophotometrists. They cover the HR diagram at corners outside the HR diagram, I think, in some cases. A lot of the other libraries that we have made available to us are either mergers of them or were produced by modelers to begin with, like Pickles and Cruz's data.
Does the NGSL give the radial velocity that they used?
No. However, Gaia does. Hence the TopCat tie. And when I said we want to augment these data, instead of having a very narrow view of what these data are, I try to put all of the Simbad fluxes in there, all of the relevant Gaia data in there. And that way you can do your analysis as you will. Well, folks, thank you very much for the time. Turn it back over to Jerry.
Oh, Jerry, you've muted yourself. Uh-oh.
Next, we're going to hear from Tony Rhoda, lessons and initial observations with a 3D printed spectrograph.
Thank you very much, Jerry. First thing to note is that GoToWebinar doesn't trust me with the controls. My wife would say that that's a euphemism for my life, but when I say, can I have the next slide, please, Bob, I haven't got a little minion running around here. It's the guys in the studio. So you should first see a slide, a splash slide, which says the role of 3D printing. Yep. Okay. This is the second paper in what looks like becoming a series of papers charting our group's progress from basic 3D printing a 3D spectrograph that works, all the way through to something a bit more complex. And we're going to be covering that in this presentation. The original paper, the first paper, was given by Jerry Foote, and that was last year at the SAS 2019. I'm not going to cover that stuff. That's the printing for dummies. That's all the holes we fell down and all the issues we had. But we did get to the point where we got a spectrograph that worked and worked quite well. And you'll see more of that in a moment. So I'm doing this because we have had significant progress, and that's what I want to talk about today. But bear in mind, please, that this is work in progress. Okay, can I have the next slide, please, Bob? So you should now be seeing a slide which says background. And just to bring everyone up to date who hasn't read the paper or wasn't at SAS, about 3 years ago, a very talented Dutch guy by the name of Paul Gerlach published a spectrograph in 3D printing files. And it took people a little bit by surprise because it worked. It did have shortcomings. Yep, it did. And probably you can guess what most of them are. I'm going to touch on them anyway, but if you know anything about 3D printing, you know some of the issues that's there. But the spectrograph worked and it produced good spectra. So about 2 years ago, Woody Sims got us all at the Flagstaff SAS session and said, we'd like to have a go at this. Let's all get together, form a little team, print the spectroscope, the spectrograph, which was now in its second iteration, the low spec 2. And let's see how far we can push this. And other people around the world have been doing this too. There's several notable people in Europe doing this. It seems to have caught on something of a cult following. So let's print the spectrograph. Let's see how far we can push it. And it's the low spec 2. You'll know that there's a low spec 3 being published. It's the low spec 2 that forms the basis of our investigations. Next slide, please, Bob. You should see a restatement of our objectives. And we've moved on a little. You know, it's fair to say we've been doing two years' work. And we've gone on from let's print a spectrograph that works to let's print a spectrograph that we can use for pro-arm submissions. That's quite a step. You know, can we do something that's reliable? We trust it to do what it says on the tin. You don't have to fiddle around and faff around with it to get half a distance spectrum. This is something that's repeatable and will work. And to do that, you need something, you know, you need to do 1000 resolution, R equals 1000 for full bandwidth stuff. But also people had been putting more dense gradings in there. An 1800 line grading gets you to somewhere near 10,000, and R equals 10,000. So now you're in H alpha territory. And indeed, that's what we did. We tried different gradings and looked at this and thought, okay, this is good enough to move on with. Next slide, please, Bob. And this is what we're going to cover in the paper. So the right-hand side, you should see a number of boxes. The blue boxes on the right-hand side are the usual suspects. These are the things that you know is going to go wrong, especially if you're a 3D printing addict. But you've got to account for them, and you've got to mitigate, not just mitigate for them, but really put them to one side if you're going to achieve that objective of a pro-arm class quality observation. So we looked at thermal expansion. We looked at mechanical issues. We looked at the usual things, the wish list that any astronomer, you know, if this was Mel Gibson making a movie about this slide, it would be entitled "What Every Astronomer Wants," because when we said, what do you want us to put in there, we got back feedback which said, well, it needs a calibration, it needs good focusing. You have to be able to focus the camera lens on the fly if that's what you want to do between observations, obviously, but you have to be able to do that. You need to be able to control the grading. There was lots and lots of stuff in there that we knew we had to do, as well as all that boring stuff about taking care of the thermal expansion. So let's restate where we were and where we were working from. Can I have the next slide, please, Bob? So you should see a couple of spectra. The two takeaway points from this slide are, we're not putting lipstick on a pig. We've got something that works, and it works well, and it's a good design. It's a classical spectrograph. It works well. So let's not throw away what's good. Let's keep what's good. Let's work on that and improve it. The second thing is, these spectra are remarkable because they're unremarkable. It's exactly what you'd expect to get from a spectrograph. So on the left-hand side there, you've got a full bandwidth spectrum of, it's an F8 star that we did. One of the Miles standard stars, so we knew what we're dealing with. I'd observed this before. And what you see there is a really good fit. My trace is in a blue. You can see the telluric lines to the right. That's the blue bit that the Miles star doesn't cover. The Miles database doesn't cover. The red overlay is the Miles library star. And you can see that's a very good fit. I'm really pleased with that, but it's what you'd expect to see. There's a little bit of discrepancy down at the blue end. That's the camera. That's mainly the camera's response down there. But we were pleased when we saw that. On the right-hand side is a spectrum of our sun. It was, the spectrograph was on a telescope mounted in the observatory. We just took that to see what we could get. That's an R equals 8,300 definition spectrum, and that's not bad going. It's obviously H alpha, it's that region, but bearing in mind that we're aiming to be able to tune this and turn that grading automatically, we can probably pick any wavelength band we want. And that spread is round about 70, 75 nanometers. So again, both, you know, it's what you'd expect to see. It's what you'd want from this, you know, what every astronomer wants. It's basic spectra without any fuss, except that left-hand spectrum took 4 or 5 attempts to get. And that's not what you want. It's not repeatable yet. It's not easy to use. So can we have the next slide, Bob? You know, this is just a splash slide. It's basically saying, so guys, what went wrong with the other 3 or 4 spectra? And we're going to delve into that now. Next slide, please, Bob. So we have an issue that you should be seeing a slide, sorry, that says thermal effects. If anybody can't see that, just let me know, guys. Everybody knows that thermal printing filament has thermal issues. It has a thermal expansion coefficient of 2 to 3 times that of aluminum, wrong side of the Atlantic. So 2 to 3 times expansion brings about some serious issues. Spectra move, so do calibration frames and all that kind of thing. You just can't put up with it. Now, at this stage, Clark Ager, one of the team, went into investigation mode. He put all sorts of sensors on this thing. He put it in his icebox. He put it out front in the sun. He brought it back into his icebox with the cables trailing, and he came up with some really interesting data, which basically said this thing expands too much. In the UK, it's not an issue. I'd made one with PETG with carbon fiber, and you know what? It performed great. But I don't get the big temperature swings that you get. And it was clear that it was an issue. Now we could get around this. You know, Clark designed a thermal box to go around the spectrograph to cool it down and heat it up if necessary, just to try and get a stable temperature. But we were basically trying to engineer out something that didn't need to be there in the first place. So we did have this issue with thermal expansion. We did try the various ways to get around it. But as you see in the next slide, we decided just to do what we should have done in the first place and replace the box or the actual material that we were printing with. And we did look at printing in metal. I mean, those printers are around now, but that defeats the object of trying to save some money by doing this. So next slide, please, Bob. Putting the thermal issues to one side, looking at the mechanical issues, again, PETG with carbon fiber, that's pretty strong stuff. It prints fine threads. They're eminently usable and very, very accurate. I had no issue with putting an expensive camera on there, but it did wear. And it didn't take many screw-ins and screw-outs for that to start to look slack. And of course, that's not what you want in a spectrograph. It's exactly what you don't want. You don't want any movement at all. So we looked at ways of, can we put an exoskeleton around this? Can we brace it? Can we do all sorts of other stuff? The answer is, yeah, you can do that. But again, you're just trying to engineer around a problem that really you don't need. So we're going to park the thermal issues and we're going to park the mechanical issues, even though you can embed T2 interfaces in there, metal interfaces, and use those to couple cameras and the telescope interface. Just park that, push it to one side, take the easy way out, and provide an aluminium box. Keep the spectroscope, the spectrograph, keep the optical the actual design of the spectroscope, because that's good, that's stable, that works, we know it does. But we have to address this problem that everybody knows there. I mean, if you've done this, you know it's there. You know the thermal issues, you know the mechanical issues. It might surprise you to note that transparency wasn't on the list of issues. Yes, PLA is transparent to infrared, but when you start printing with the more expensive filaments, that goes away. It's a non-issue. It's not there. And it's not addressed in the paper because we didn't find it was an issue when you're printing PETG. So next slide, please. This is the initiatives. We've got rid of the boring bit now of doing what you have to do to make the design stable. This is the interesting bit. So we have, the first thing we needed to do, do we have a slide which says calibration box? Yep, okay. So the first of the initiatives was a calibration box. Every spectrograph needs a calibration box in order to calibrate your spectra. Now, most commercial spectroscopes, most commercial spectrographs rather, use a Relco bulb. This is a small bulb that's found in neon starter tubes in Europe. You've probably got them in the US. And it contains argon and neon. And it's great for calibrating the wavelength of your spectrograph. So we just decided to hunt around and see if there was anything else. We tried mercury lamps, we tried all sorts. We tried about 5 or 6 different Relco type lamps, and we came all the way around to where we started and settled on the same old Relco lamp, with a difference though, because we tried several different circuit designs. And in the top right hand corner, you'll see a design which featured in Richard Walker's book, which we liked most. We tried 3 or 4. They all worked, they all did the job that they were supposed to do, but the Richard Walker circuit is tunable to some degree. And when we used it, we found we could light all the electrodes in the Relco lamp, and it was very, very bright. It was a superb calibration spectrum. So Clark again didn't design, he modified that circuit that you see in the top right to suit some of the component issues that you've got in the US, getting some of the European transformers, that kind of thing. So that is a slightly modified design, and it works great. And we've decided to settle on that one. The device you see in the bottom right was designed by Jerry, and it's a device for inserting a screen into the spectrograph in front of the slit through which to project the Relco lamp, so that you can project the Relco lamp straight into the spectrograph. It works, it's beautifully simple. The best designs obviously are, and it lends itself to automation, which is a continuing theme here. So you have a calibration box that works, gives good spectra. The spectrum on the left that you see there goes all the way down to the 3850 angstrom line, clear as day, all the way up to 7723 angstroms. Everything you need to provide a good calibration. That spectrum, if memory serves, has an R value of 1250. And I think a quick calibration in BAS software gave me 0.085 RMS in the calibration equation. So that gave us that's very heartening to see when you can do that. So one other person deserves a mention. When we're talking about automating this stuff and inserting the screen and turning the circuit on and off and all that kind of thing, we were throwing all this code requirement over the fence into Tom Smith's backyard, and he was saying, yeah, that's a no-brainer. We can do that easy. So we were building a bit of a momentum here. We were learning to do new stuff to provide basic facilities for a good spectrograph, and we were coding for it, and we were paving the way for remote control and automation. Can I have the next slide, guys? Now you should see guiding and focus. Every astronomer wants good guiding and good focusing. And every spectroscopist and every spectrograph you've ever seen probably provides quite poor guide images. So first and foremost, we played around with the guide image lens. We've tried 4 or 5 different designs. That's work in progress. We're absolutely sure we can get better field of view and better images. We're just deciding which one we're going to go with. As far as focusing is concerned, there were 2 issues. When you move stuff, things tend to move out of focus. Every spectroscopist knows this. So we want to be able to focus the camera lens, and indeed we've decided to replace the camera lens from the low spec. Jerry came along and just said, look, we can get a commercial lens for f1.8, f2. It costs $50 and it's a better lens, and it also solves the problem of trying to project a curved focal plane onto a flat chip, because what we found was we were getting very slight defocusing at the edges of the spectrograph. And we wanted to put that right, and that's the easiest way to approach that. And of course, it adds to the ease of automation. We can automate that quite easy. Next slide, please, Bob. So you should have now something that says grating adjustment and a neat little diagram down there. What we wanted to do was address something that came up during the thermal investigation phase that Clark found out, was that when things move, the micrometer, which controls the actual grating, it's made of metal. It wasn't expanding. Everything around it was expanding or contracting. So you got a natural movement in the turning of the grating, which again caused spectra to move. We needed to get rid of that. So Jerry came along and said, you know what? Take away the micrometer. We've got more room now in the box to play with, because we don't need all that buttressing that the 3D body needed. We've got a lot more room to play with. We can put a small motor in there, control it remotely, give it a direct drive to the turntable. Paul's design is very clever. He produces a small turntable onto which various types of grating can be fitted. So we've got the turntable to play with, and we can direct drive that. No belts, no backlash or anything like that. Quite accurate. Tom Smith, of course, said, hey, you know, dead easy to write code for that. He came along and dropped a neat little window on our screens, which said, control this, control that, in, out, move it all about, that kind of stuff, which was very heartening to see, because it meant we could start to control all these different aspects of the spectrograph and turn it into something that was very usable and very light touch. Okay, so there's an idea for the grating adjustment. Can I have the next slide, please, Bob? So we're now at the point where we're talking about remote control. Actually, Bob, can you flick forward onto the one that says we'd consider the pi? I want to do that one first. This, you're not meant to read this slide. It's just showing that Wayne went away and said, yeah, I've taken Tom's code, we can do this. We're going to use a Raspberry Pi as the main PC, and we're going to run little Arduinos, nanos, to run the individual boxes around the spectroscope, the spectrograph. Because anybody who does this kind of thing will know that we're proposing to automate most of this, and we've just added 10 to 12 cables coming off the mount. Well, if you can't take all those cables to the PC, you take the PC to the mount. And we thought that's a good thing to use. We use the Raspberry Pi and all these little Arduinos. Can you move back, Bob? Can you move back to the one that says camera and instrument remote control? So here we get rid of the cables. Wayne had been talking to John Hoot, both of whom you've already heard from. John was doing something with a little computer called an Odroid, and that's like a big beefed up version of a Raspberry Pi. Very powerful, very light. And Wayne started to say to us, look guys, this automation is going to work because this is very light. You can mount it on the OTA, and you can have one cable, one Ethernet onto that mount, and one power cable, and we can start to run this remotely quite easily, and we have the telemetry to do it. Okay, and I think we're now, I'm sure Wayne will correct me, I think the small modules that we're using for the individual units are now the BLE 33 Sense, which have accelerometers on it. We're now thinking about, you know, we know where your scope is pointing. We know what the mount's doing. Now that's maybe for another day. That's for the third or fourth iteration of our spectrograph, but we can do lots more with the telemetry and the automation that we're putting on there. It's got lots of bandwidth, lots of real estate that we can use. Next slide, please. So, sorry, and again, you should be looking at multi-rig capability. So we're feeling quite good about ourselves. We've designed these units. We have very high confidence. We know they're going to work. We know we've got something in an aluminum box with a good design. This is starting really to take shape. And this voice sitting quietly at the back, and you know who you are, Woody Sims, the sanity checker, who is a very, very good spectroscopist and produces some very high quality work. He said, you know what, I'd really like to be able to control the photometry rig that I've got on my scope as well, because I do simultaneous photometry and spectroscopy. And Wayne said, yeah, sure, we can do that. Why? Because this is modular and there's tons of bandwidth in that little Odroid box. So it won't be available on our first release, but here you have something that is capable of doing more than just our spectrograph. Now, I don't want people getting excited. We're not going to start controlling mounts and all that kind of thing. But what we have is something. Is that the 5 minute, Jerry, or are we on time? He's waving. So can I have the last slide, please? The outcome. The outcome is a usable box. I mean, I'm not. You can read. You can see what's on there. We've got a low spec. It works. It's fully automated. It will be capable of remote control. We're absolutely confident of that. You know, there has been issues to overcome. We've done some other stuff. There's a whole bunch of stuff in the background that we haven't even touched on, and not even in the paper. Last slide, please, guys. The conclusion. This is the one thing that we need to pull out of here, and that is, when we finish with this, however far we get, Wayne's going to put all this into a GitHub, and we're going to have everything that we do is going to be accessible by all you guys. We publish everything. It's part of the learning process. It's part of giving back. We've had great fun doing this. We're still meeting and pushing this along, sometimes twice a week. It's been a delight to be part of. And with that, Jerry, I'd like to hand back to Bob in the studio.
Thank you, Tony. That was very good. Do we have some questions? Chat or raised hands?
Hard to believe that there aren't any. There's
was
still
the answer.
128 people in the audience. Some of you guys must have a question, and gals.
If not, stick around. If someone comes up with ideas later, we'll answer that later.
Okay. Tony, thank you very much.
You're welcome. Thank you.
May the sun shine on you. Or is it going to be clear tonight?
You know what? I mean, I really do run down this island that we live on for being a cold, wet rock, but we've had glorious sunshine for the last few weeks. It's really tough enduring lockdown. Thanks for asking.
Those of you in the audience may realize that Tony's in the UK.
I'm working blind.
Thank you.
Well, Jerry, I guess I propose that I turn the panelists' webcams back on and see if that prompts any further questions.
Okay.
It wasn't clear to me. where you ended up on the enclosure. Are you still 3D printing, or are you putting it in an aluminum box?
We're using
Um,
a, go ahead, Tony.
Go on.
We,
Well, you know something. In the UK, I was using a printed 3D enclosure, and it was working, but it was difficult because of what Clark did. It just became obvious that we need an aluminum box. And that's what we're using.
But you're using 3D printed assemblies mounted into the aluminum chassis.
correct.
Absolutely right. And you know something, that's where the 3D printing technology is really strong. We can play around with the different lens holders and all that kind of thing, and change that kind of stuff real quickly. And don't forget what Paul did originally with that optical train and the holders and everything. That's still all intact inside the box because it was a very good design.
So
The box,
you've
the box
picked
is
a standard box then from some manufacturer.
it's a die cast aluminum box. Die casting it makes it it's a pretty sturdy box, and it's from a standard manufacturer. And one of the things as we go on through these changes is Paul's original design idea is low cost, so it's accessible to anybody.
And we don't have to print as large of assemblies. A much smaller platform will
That's
right
the
on.
components. Yeah.
correct. And the aluminum box actually is cheaper than the filament it would take to print the big box, the normal print box. So,
The answer hits you in the head. Yeah.
Okay, we have one question from the audience, and that is why not use a fiber optic and have the actual spectrograph be off of the telescope? The main problem with a fiber optic comes down to, well, they're fiber optics to begin with, is you still need a guide head and so forth up on the main assembly, and literally the rest of the weight doesn't matter too much in that regard. The other thing is getting a decent sky measurement. That kind of comes along with the long spectrograph, but not so much with the fiber. So we would need two fibers essentially to capture sky for the contaminant background and for the actual signal itself.
also, there's an issue of most fibers that are commonly used are in the 50 micron range. Our slits are typically in the 20 micron range. As soon as you put a 50 micron source into your spectrograph, that changes your R value. You have to rechange the geometry of the spectrograph in order to handle that 50 micron input image.
And what we've got, I mean, we have something that's still very, very light anyway, and very, very compact.
Yeah.
You know, you're talking about a 6x4x3 box. So it's very light to start with.
We also have a question from Albert Smith. Do you anticipate commercial opportunities?
As Tom, okay.
We'll sell you the rights.
The short answer
All
is
the work's
no.
on GitHub.
Actually, the whole idea of GitHub is so it's there for anybody that wants to build it can have at it.
Yeah, you've been talking to Stan Watson, haven't you? I think, you know something, it's the whole philosophy of this, and it's what Paul started 3 years ago, is it's free to all. The whole point of this, there's some really, really good, some superb manufacturers already in the market. Why get wrapped up in that? This is low cost. This is, you know, we're not in competition. So it's low cost. It's an educational device to start with that builds into a pro-am class spectrograph. We are not in competition with those guys. Can't match them.
Oh, in the absence of other questions, I have another one for John Hoot. The Beware, Rachel Freed and Calais Talk are on here, and your talk made it seem to me like there is a whole gang of possible student research projects hidden in Gaia, and I wonder if you have any suggestions for their kids.
I'll be glad to take that up online with them. I didn't do my usual astrophysics workshop this summer, but I keep a list of known as the projects for Manic Astronomers, and I would be glad to share them with them. And yes, I've added a number of things to that list, which are at least Gaia inspired or Gaia assisted observational projects.
Great.
Yeah, John Hoot didn't bring up this up in his talk, but there are some interesting possibilities for extragalactic work with Gaia as well, because I had a student last summer do some work on identifying red supergiants in M31 and M33 using that, because of course those should be beyond the parallax capability, right? So there are even some interesting outside the galaxy things to do with Gaia as well.
Yes, for those of you in the southern hemisphere, the Magellanic Clouds actually have some real interesting and useful data for that as well.
Okay, I also have another question for Dr. Martin. The comp stars that you've all identified, I assume, are in the Milky Way galaxy. They're foreground.
Well, we haven't determined that. That was not part of the process. I have not done any digging in Gaia to see if they are or not. From the color cut, there is a chance you are getting asymptotic giant branch stars in there. And so it's not guaranteed that they are all in M31 and M33.
Okay, what I was getting at is the risk of the extinction in the galaxy, resulting in odd color effects compared to your comp stars if they're in the Milky Way.
Yeah, so the extinction effects within those galaxies are not really huge to start with, particularly when we're talking about the brighter stars that are unobscured. And the color cut we took initially would exclude most very odd cases, right? That color cut we took with B minus B between 8 and 0.8, which is recommended by the International Chart Working Group, eliminates a lot of those oddballs that might crop up.
Cool, thank you.
John, one of the things that we did with the event back at M51 last year was I was able to dig out of Hubble original images with that really crisp ability to see into the galaxy. So we could just kind of look along the line of sight to see if it was lumpy and cloudy or clear. What I found was there was an open cluster that was down in the area of our target. It's anybody's guess whether they were related, but it did give me that clarity. And then the second thing that you can do with Gaia is Gaia produces the number of observations that they made of that particular star. So you can say, show me things that have a magnitude error less than something that has a large number of observations. And that kind of guarantees that you've got a pretty good comparison star, that it's not wiggling around on you from observation to observation. Well,
I guess it's time for me to ask our final poll. Those of you in the audience will remember that I mentioned after the conclusion of this webinar, about a half hour from now, we're going to start an after hours online reception, live mics and webcams for everybody, and a free-for-all discussion. I believe Wayne's got it set up so there will be a multitude of rooms available for groups of a dozen or 2 dozen people to talk about whatever they want. But I thought it might be fun to give you an opportunity to weigh in on what you think the discussions are that you'd be interested in. So I am launching a poll about what topics you would like to discuss during the after hours reception. You can click as many of those boxes as you wish. And in a couple of minutes, I will share the results. For those of you who do want to attend this after hours reception, don't forget, go to the handouts box on your webinar control panel. You will find a handout called the after hours reception PDF. That includes the Zoom link that will take you in there, and it'll start, I think we said at 1 p.m. Pacific Daylight Time. What is that, 2200 UT? And I see people are still clicking buttons on the poll. This is like watching pari-mutuel betting. The numbers keep changing as one of you clicks another box. Yes.
Bob, I
Yep.
want to point out that the announcement says 2100 UT. That's posted in the handouts.
Okay, what's a half hour from now?
I think half hour from now is 2100, right?
Yes. So that must be the correct time. Okay, let me see. I'll close the poll, and just for fun, let's see, we got half of you have voted. I'll close that and we'll see if I can share. I can share the results.
I love the way we're amazed at these tools.
Hey, you know, if we were teenagers, we'd have this all figured out. Okay, so
We're
it sounds
amazed
like
when they work.
okay, so it sounds like there's a little bit of everything. Wayne, bear that in mind, I guess. And at that, and my one final reminder is, if you enjoyed today's session, but you have not yet registered and paid for the next 4 sessions, which occur in June, there is still time for you to do so. Go to the SAS website, click on the Symposium tab, and the registration link is down below, and we look forward to seeing you all then. Stella, have you returned, and should I unmute your camera? No, I think.
I am here.
Oh, great.
I'm here, but my network is not reliable. So
Do you have any parting words of wisdom?
parting words of wisdom. I really enjoyed day 1. I have to say, though, I'm really impressed by do-it-yourself spectrographs through 3D printing. At this point, the future of non-professional spectroscopy is really bright, and I'm looking forward to seeing data from those printers, from those instruments. So with that, thank you all for attending. It's been an awesome first day. We set a high bar for everyone. And thank you again to the production team for being so efficient. We'll see you in 2 weeks.
Yes, on June the 13th.
On June the 3rd.
And to our presenters, Tony, John, Wayne, and John, thank you all very much. This has been entertaining and enlightening.
Glad to do so.
Absolutely. Well, to all of you, thank you again for joining us. Please stay safe. And same time, same place.
Yep. Okay, I guess I will pull the plug on this first day. Thank you all. Have a good afternoon.
See you in Zoom.
Yep.
Bye, all.
Oh, John just left. Pradeep Karmaka, if you're still on, you've asked a question about any project on long-term period change study in Gaia. Oh, John is still here. Would you like to try to weigh in on that? I'll see if I can unmute Pradeep.
Yes, I'm unmuted. Good. The answer is yes. They have a category of variable where they say we know this is variable, but we don't have a period for it, but we're seeing either significant variation or we've seen transients. Those are targets of opportunity for those of us in the small telescope science community. They've clearly flagged things that wiggle, but we haven't looked long enough at them, and so they're very likely either long period stars or they're eclipsing systems wherein their sampling cadence doesn't pick up the relatively short transients.
Hello. Hello, I am Pradeep Karmaka. John,
We hear you,
can you
Pradeep.
hear me?
Yes.
Can you hear me?
Yes.
Yes.
Can you hear me? Yes. Okay. Welcome to all of you. Actually, I'm from India. At present, my situation, I'm a teacher of an institution in the field of mathematics. But anyhow, I'm very much interested in this field, mainly light curve analysis of RR Lyra and Cepheid's long-term period change analysis. So I am very much interested if there is any possibility to join this type of project work. So that is why I sent this question. And I am also interested about respected Tony Roda had said about the spectroscopy. I am little bit knowledge about IRAF. So if there is any chance to study the spectroscopy analysis, then I very much thanks to you. And I'm glad to share with you, I have become a member of AAVSO in the year 2018 December, with the help of respected I hope all of you know him, respected Horace A. Smith. I have at present I am doing a work with him on M10 variable 2 Cepheid. There in M2 we have three types of variable stars, P1, P2 and P3, but we have enough data to analysis P2 and P3, and we are on the way of this work. So if there is any possibilities to do work in the long-term Cepheids period change analysis with respect to Geiger archive dataset, and one more request to respected Tony Roda, that I am also very much interested to spectroscopy analysis of RR Lyra and Cepheids if possible.
Wonderful. And with luck, we'll see a paper from you in either the AAVSO future meeting or SAS or in the journal.
Pardon, please, sir.
Okay, Wayne is telling me that I really do have to close this so that he can open up the reception. So
We'll take a brief break in between. Let's put it this way. I will take a brief break in between.
So we're out of here. Hey, thank you very much, everybody. We'll see you in a little less than half an hour. Bye-bye.
Bye, y'all.
Okay, thank you to all of you.